Hello everyone, this is Sandeep and I'm currently pursuing my third year electrical engineering in IIT Tirupati. And I'm here to talk about my mini project, Cloud Motion Estimation from Machine Learning for Image Processing course. So let's talk about a basic info regarding the Cloud Motion Estimation. It plays a very crucial role in weather predictions all around the world by tracking its direction of motion, giving us predicted destination of it at a particular instant of time. This uses satellite cloud images in order to study the characteristics of the cloud, which contributes in forecasting the meteorological parameters. Our aim is to propose a fast and efficient block matching techniques from the various motion tracking techniques in order to detect the direction of cloud motion. So coming to the main objectives. The main objective is to work on the improvised architecture for cloud motion estimation using deep neural networks with a modifier error function for training our proposed networks, and then to make a quick comparison of our proposed network with other existing techniques like the FlowNet, T-Flow, etc. So let's talk about the basic motion estimation techniques. The general definition in one word is to track the direction of motion of the objects in the frame, finding them by using finding the key points using different frames in the video sample for every interval of time t. So the common methods which we use in general for implementing the motion estimation are the artificial neural network, deep flow, and the FlowNet. So let's have a look at the steps for implementing them. Firstly, we find the key points of the image in the video sample for every time t. Then we try to match the key points for all the image samples using a common and efficient technique called ORB, which I have explained about it in my earlier presentation. Then we find the optical flow from the key point features of the images. Then we get the vectors describing the direction of motion of that object. But these methods won't be helpful to find the cloud motion. The main reason was that none of these networks are originally designed for non-rigid motion. They were basically trained and tested for rigid body motions only. So as mentioned earlier, we will be proposing a network designed for unsupervised data sets using convolution networks, which is a quite effective and easy to handle. Before looking into the aspects of the network design, let's have a look at some of the existing architecture involving on the basis of CNN, which is the one refined net, which is introduced to introduce the importance of the resolution dealing with image data set and a work around with higher resolution images that can be fed again in the neural networks for a better capture of details. The autoencoders. It shows the importance of downsampling followed by upsampling in the network. Also, the idea of going for compensate going for the unsupervised learning to compensate for data sets is seen in RBMs and VAEs. And the flow nets. Though being the most basic method used in the DNNs, the idea of using CNNs for optical flow in flow nets opens a new field where CNNs are used not only for the classification, but for more complicated problems such as the motion detection. So let's talk about the error and or the loss function for our proposed network. We find the equation of loss function on the basis of two assumptions, which is the brightness consistency and the smoothness constraint. The brightness consistency says that the object in the images before and after time t has same intensity, which is the I intensity at a particular time t is same as the intensity after time t for that particular object in the image. So from that we get the equation uix plus vifi plus it equal to 0, where ix and iy are the gradients along the xy directions of the image plane, and it is the frame difference between the first and second images with respect to time. And purely vectors are the variables describing the direction of motion of the cloud, and using Lucas-Canade method in one word, we get the formula UV in representation of the matrix representation, which we find the squares of the gradients of along the patch and sum them up and substitute them in this matrix representation, and we get the values of values U and B. And after we get the variables, we get the error loss function, which is the square root of the sum of gradients ranging from 1 to m and a constant c summed up along with it, which is basically equal to 0.001. That the epsilon value basically deals with the error loss function equation, whether to use L1 norm or L2 norm. So in our case, we use L2 norm. So we coming to the data set and training. The flying chairs and things 3D datasets are used, which contains rigid body datasets. Then we test our proposed network and compare the results with other optical flow techniques like the D-flow, FlowNet, LDOF, etc. And considering the rigid body motion dataset, which is UCF101 dataset for validation, and the MP1SC Syntel. From the results, we can see that our proposed network shows similar performance compared to the other techniques, but yet the other techniques shows better result than our proposed network. That is due to the fact that our network is basically designed for unsupervised network design. So in order to deal with non-rigid objects, which is why the AE values for our proposed networks is higher when compared to the other algorithms. So coming to the non-rigid data sets, the cloud images data sets are taken from the European Center for Medium Range Weather Forecast. We can see that the time flow, we can see this time FlowNet 2.0 and our proposed network performed better compared to the other two algorithms, and yet FlowNet 2.0 algorithm performed better when compared to our proposed one, because the average time required for processing one image frame is more than 100 milliseconds in our network, and the accuracy reached by the FlowNet is only after extensively training the supervised data, whereas our network is basically trained using very scarce data set. So if we use FlowNet 2.4 when exposed to unsupervised data, we can directly say that our proposed network performs much better when compared to FlowNet 2.0, because our network is basically designed for unsupervised datasets. So let's have a look at the visual representation of all the algorithms. So the first column represents the input images, and the second column represents the output which we extracted from using the deep flow algorithm, and the third column is the output which we got from FlowNet 2.4, and the last column is the output which we got from the our proposed network. So let's have a look at a basic coding of tracking the image of the rigid objects using optical flow. So this is the optical flow estimation code for rigid bodies video sample. So as we can see, the algorithm started to trace out the direction of motion of the cars and showing the color, the indication showing the direction of movement of the cars. So for the reference, I used optical flow, feature extraction, tracking algorithm, and the FlowNet algorithms, which is basically found in the OpenCV library. Thank you.